Resonance and formal charge. Some molecules have more than one valid Lewis structure. Now, a couple slides ago, we looked at one where we could draw two good Lewis structures, but we're not sure if one's maybe better than another. Sometimes you can draw two different Lewis structures that are actually equally valid. So let's do ozone. Ozone is O3. It's like supercharged oxygen. So here's one oxygen, and here's another oxygen, here's another oxygen. So instead of drawing dots and then sharing, let's use our rules. So these are probably going to have to be in a line because we're not going to deal with circular compounds in this class. So 3 oxygen atoms. How many valence electrons? 18. Each has 6. 3 times 6 is 18. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18.
Why didn't you put a dot on the bottom of the middle?
Well, I can't just put 2 dots here because I don't have enough electrons to do that. So I did my best, and now we look at this and it's like, no, the oxygen in the middle isn't happy. So what do?
Make some bonds.
Make some double bonds. So let's take this electron pair and put it in here. Everybody happy?
Almost. Make it a little
Why
more
not?
symmetrical.
Well, how can I make it more symmetrical?
Erase the
So this one's got 8, and this one's got 8, and that one's got 8. Right? But this oxygen is saying, well, why did I have to share more with you? Why does he get to have 3 lone pairs all to himself? Well, why? Because I randomly chose him? Couldn't we also draw it with the bond to the other oxygen atom? Is there really any difference between those two? So how can we say that one's better than the other? We can't. There are 2 valid Lewis structures. But the true structure is neither of them. How's that? The Lewis model has some limitations. Actually, ozone exists as an average of those 2 Lewis structures. And what we observe in experiments is that we don't have a single bond and a double bond. We actually have 2 bonds that are the same. They're kind of intermediate between 1 and 2. So they're like 1.5 bonds. And so what we do to represent this is called resonance. I should have drawn those down here. I could move them, but that might be more complicated. I'll just draw them over again. So what we do is we say that it's between these 2.
Yeah, how will we know when it's more than one structure? Like, say in Western chemistry, if we were doing something like this, how would we know?
How would you know that there's 2? Well, that's a good question.
Would you just like draw as many?
Generally, resonance structures involve multiple bonds. Multiple bonds between the same atoms. And so here, we have to put a double bond in here. We can put it between the central oxygen and this oxygen, or the central oxygen and the oxygen on the other side. And we're just putting the double bond between 2 different atoms that are the same element. And that's where you see the resonance. So this is how we represent that. We draw both of the structures with a double-headed arrow. Sometimes there's 3 or 4. And so you just line them up and you put double-headed arrows in between them.
It's a lot of work.
It is a bit of work, but it's how Lewis structure gets around one of its limitations. So the actual structure is called a resonance hybrid. And we can think about dogs. So if you took a German Shepherd and a white golden retriever and bred them together, what would their puppies look like?
Beautiful.
Probably beautiful, but they'd look like a combination of the two parents, right? When we draw this resonance structure, a misconception that students sometimes have is that it's flipping back and forth. It's this and then it's that, and it's just going back and forth. That's not true. This puppy is not going back and forth between German Shepherd and Retriever. It's always the same. It's an average of those. And so here's one Lewis structure, here's the other Lewis structure for ozone. The true Lewis structure is more like this, where we have this single line and then a dotted line, and that's an attempt to illustrate a 1.5 bond. So we draw the individual Lewis structures with double-headed arrows, and then we understand that it's actually an average of those structures. One of the problems with the Lewis model is that electrons are localized on individual atoms or bonds between two specific atoms. And in actuality, many molecules have electrons that are delocalized. They're shared over the entire molecule, not just between two atoms. Lewis structure can't deal with that.
You want to draw the valence on the resonance hybrid structure?
Well, it gets a little tricky.
Because you don't know
Because,
where they are.
yeah, you don't really know where they are, right? So, here you've got 1, 2, 3, you've got 6 lone pairs. Well, how do you divide those up when you've got 1.5 here? It gets a little
6 on
dodgy.
each end and none in the middle.
Yeah, it doesn't work very well. And that's why we don't draw it like this. In the Lewis structure, we draw the individual structures with a double-headed arrow. The electrons get delocalized like this, spread out and shared over the entire molecule because this lowers the energy of the molecule and makes it more stable. That's called resonance stabilization. The word resonance implies that it's resonating between, but it's not. It's really just an average. Okay, so let's draw a Lewis structure for the NO2 minus ion. What's the name of that? Nitrite. Right? It's one less oxygen than nitrate. Include all resonance structures. So if they say that, there's going to be at least 2, and you need to find them. Yeah.
Real quick on the previous one.
Mm-hmm.
Why don't you just have 2 double bonds to the middle oxygen? And then 6 valence on each of the outside ones.
Well, because that's not what happens either.
Okay.
Yeah.
I was just thinking, equally shared, each one's making 2 bonds. Oh, that's 4 bonds. Gotcha.
Because, yeah, that doesn't work either.
Gotcha.
Okay, so NO2 minus. Well, we've got nitrogen and 2 oxygens. How do we connect them? Well, we can think of electronegativity. Which is more electronegative, oxygen or nitrogen? Which is closer to fluorine? Oxygen. So the oxygen is going to be on the outside. That means that the nitrogen is going to be in the middle. Wrong pen. So nitrogen, and we're going to put the oxygens on each side. How many valence electrons total for this ion? Well, nitrogen has how many?
17.
Valence electrons. 5 valence electrons. You're jumping ahead of me, huh? 2 oxygens each has 6. And the minus, you add 1. So we've got 12 plus 5 plus 1, 18. We're close. So then we start putting electrons around. 2, 4, 6, 8, 10, 12, 14, 16, 18. We need a double bond. Nitrogen is bonded to oxygen on each side. We can do the double bond with the oxygen on the left, or we can do the double bond with the oxygen on the right. Those are our 2 Lewis structures, our resonance structures. Yes?
Could you have drawn the dots under the N under the other O?
I could have, yes. Yeah, I could, this is just our rough draft. I can do it like that too. It's still not happy. And so now we have to choose, well, which oxygen's going to share its lone pair? Well, let's look at both of them one at a time doing it. So take that one and put it in here. Does that satisfy the octet rule?
Mm-hmm.
Yep. Now, we need to put brackets around it. And it has a charge. And then over here, what we're going to do is we're going to draw it with the double bond to the other oxygen. Sorry, I'm going to sneeze. And a minus in there. Do you see how they're the same but different? And then we put a double-headed arrow. I made them kind of large, I'm not sure why. Double-headed arrow. So two resonance.
See that one that you showed us before, where they're got double bonds on each side, just with dotted lines.
That's a good question. What about doing it like this? Is that what you're asking?
Yeah, and then the top would be dotted.
So that's 2, 4, 6, 8, 10, 12, 14, 16,
No.
18.
The one where with the.
Oh, the dashed lines?
Sorry about
Oh,
hybrid
sorry.
structure. I think that's where we're going. I just think we haven't gotten there yet.
Well, yeah, so, whoops. So this is what you're asking about.
Yeah.
Yeah, we don't actually draw it out like that. Because, so this has 2, 3 electrons, and 3 here, 6, and so I guess you'd have to put 2 there. It just doesn't work out very well. 2, 4, 6, 8, 10, 12, 14, 16, 18. This is not, this is not a good representation either, because these electrons are paired. And so for Lewis structure, I mean, we could argue about maybe there's a better way, but this is the best way they came up with, and that's what they do. So this is really more like what it is in terms of the bonds. It's 2 equal bonds. It's not 1 double and 1 single.
Will there be an example where it's more than 2?
There will be, yes. Well, an example in the PowerPoints, I don't know. Let's see. Nope. I think we'll come to one after we talk about formal charge. Okay, so formal charge is another kind of made-up thing, kind of like the oxidation states that we talked about earlier. This is a made-up concept that helps us choose between different Lewis structures to say which one's better. So the formal charge for an atom in a structure is the charge it would have if all the bonding electrons were equally shared between the bonded atoms. So this is a fictitious charge. It's not an actual charge. We calculate this ignoring electronegativity. So one way to do it is to look at an equation like this. The formal charge equals the number of valence electrons that element has, minus the number of non-bonding electrons and half of the number of bonding electrons. If you like that, you go right ahead and use it. I find it confusing, and I find that my students find it confusing. So I'm going to show you a little bit different way to do it. There are some rules here where we use those formal charges to decide on a Lewis structure. So if you're doing it correctly, the sum of all formal charges in a neutral molecule has to be 0. And in an ion, the sum of the formal charges equals the charge on the ion. We prefer to have small or 0 formal charges. So when we're comparing two Lewis structures, we identify the formal charges, and we're looking for the one that has the smallest or 0 formal charges. Sometimes you can't get them all to be 0. There's going to be formal charge. And then the formal charge should reside on the most electronegative atom, which kind of makes sense, right? The most electronegative atom is the one that's most attractive to the electrons. And so when we have these kind of extra electrons, we want to put them on the more electronegative atom. So hopefully we'll have that make a little more sense looking at some examples. Okay, so here is hydrocyanic acid or hydrogen cyanide. And these are the two different structures that we can draw for it. And I'm going to draw them down here too, just to make them larger and so I can write on them, but not that large. So we can do it this way with carbon in the middle, or we can draw it this way with nitrogen in the middle. And we need to choose between them. So what formal charge does is it says, well, let's look at this hydrogen atom. The hydrogen atoms don't end up causing any trouble at all, but we'll look at them anyway. The way I look at formal charges is I just draw a line through all the bonds, splitting them equally. Oh, I meant to do it on the other one. Got lost. So for hydrogen, we're going to look at the number of valence electrons hydrogen atoms have compared to the number of valence electrons that the hydrogen in here owns. So this is like these, these two atoms get divorced, right? And they're going to split the property equally, regardless of whether that's actually fair or not. And so this double bond of two electrons, each of them gets one. So in this compound, with this structure, the hydrogen owns one electron. How many valence electrons does hydrogen have when it's all by itself? One. So, number of valence electrons, and then it does all this crazy math, and you end up with 0. So, it has negative 0?
What's the pink negative 0 for?
Oh, subtracting 0.
Oh, okay.
So my way of doing it is 1 minus 1 equals 0. So hydrogen by itself as an atom has 1 valence electron, and I'm going to subtract how many electrons it owns here. So how many valence electrons does carbon the atom have? 4. And how many does it own in this structure? 1, 2, 3, 4. So 4 minus 4 is 0. So this carbon has a formal charge of 0. Then we look at nitrogen. Nitrogen atoms have how many valence electrons? 5. How many electrons does it own? 5. There's 2 here, and half of those bonds, 1, 2, 3. All the formal charges are 0. That's probably the winner. Let's look at this other one. So hydrogen, the atom has 1. It owns 1 in this structure. That's 0. Nitrogen. Nitrogen atoms have 5. How many does it own in this structure? 4. So that's a +1 formal charge. Carbon. Carbon has 4 as an atom. How many does it have in the structure? 5. And so its formal charge is -1. The formal charges still add up to 0, but this one's better because we have 0 formal charges on everybody. This one is not as good. So based on formal charges, we predict that this is the correct structure. These are not resonance structures, right? Because the atoms are arranged differently.
What exactly is a resonance structure?
A resonance structure is different only in the placement of some of the electrons. So any questions? Yes?
Could you look at electronegativity and be like, okay, the least electronegative is probably going to be on the left or the right, and most electronegative is probably going to be the one?
You could look at this and use that rule that the more electronegative element is probably terminal, and predict that the nitrogen should be on the outside and the carbon on the inside. You can also look at that thing I showed you about the number of bonds, and see here carbon has 4 bonds, and here nitrogen has 3 bonds. That lines up, and we'll see that that is actually related to the formal charge.
Does resonance structures rely on the pairs and not the lone pairs? Or the bonds not pairs?
The resonance structures generally involve bonding pairs of electrons just being between different atoms. The reason that these are not resonance structures is because the bonding order is different. Here you have carbon in the center, and here you have nitrogen in the center. And so you can't really average that because it involves moving atoms. So let's do another example. Assign formal charges to each atom in the 3 resonance forms of N2O. And they're telling us that nitrogen is central, which is not what we would necessarily think, but nitrogen is central. Which resonance form is likely to contribute most to the correct structure? Okay, so we're supposed to draw 3 different structures here. Nitrogen's in the middle. So nitrogen, nitrogen, oxygen. They're basically telling us how they're connected. So we're going to have that one, and we're going to have another one like that, and another one like that. So how many total valence electrons are in N2O?
16.
16. Each of the nitrogens has 5, 2 of them, so that's 10 plus 6, so 16. So I've got here 4 already in the bonds. 2, 4, 6, 8, 10, 12, 14, 16. So we need some sharing here, right? So let's try taking a lone pair from the oxygen and sharing with that nitrogen in the middle. Now the center nitrogen is good and the oxygen's good, but the nitrogen over here on the left is still not happy. So let's take this lone pair from the nitrogen and move it over to be a bonding pair. This nitrogen has 8. The nitrogen in the middle has 8. The oxygen has 8. That's a valid Lewis structure. Well, what else could we do? They're like, well, they're both double bonds. What if we had one single bond and one triple bond? Could we make that work? Let's try a triple bond here and a single bond there. So we've got 2, 4, 6, 8, 10, 12, 14, 16. There we go. So we've got this one, and then what about putting the triple bond on the other side instead? That's the other possibility. Putting the triple bond over here.
Does that one work since nitrogen only has 5 valence electrons usually?
Well, one of these is going to be better than the others. But these are resonance forms because the difference between these 3 is just moving the multiple bonds around. Yes?
So this question said, it specifically tells you how many resonance forms there will be. Will there be questions that won't tell you how many there are?
There may be questions where they don't tell you how many. And then you have to be a little creative and think, okay, what else could I do here? The thing with something like this is these resonance structures are quite different, right? Because it's not just moving a triple bond between nitrogen and nitrogen or nitrogen and nitrogen. Here it's a different atom. And then here we have 2 doubles versus a single and a triple. So one of these is probably going to be better than the other. And it's like when you breed 2 animals, sometimes one breed, you know, maybe the German Shepherd has more effect on the children than the Retriever does. I could show you pictures of my children and you would immediately know who they favor. They look a lot more like their dad because Japanese genes win out over Swedish genes. You know, brown hair, brown eyes. I did have some influence though. So what we're looking for here is which one has the best formal charges. That one's going to have more contribution to the correct structure. So we'll mentally, or actually physically, divide up these bonds. Just cut them in half and figure out what the formal charges are. So nitrogen atom has 5 valence electrons. How many does it own in this structure? 6. So this has a -1 formal charge. Here's another nitrogen. 5 minus, how many does it own? 4. So that equals +1. And here's the oxygen. Oxygen has 6, and how many does it own in the structure? 6. So that one's 0. So we've got -1, +1, and 0. And then we come over here. So again, we've got 5 minus, it owns 5. 1, 2, 3, 4, 5. So that one's 0. And this one owns how many? 4. So that's going to be +1. And the oxygen is 6 minus what? 7. So this is -1. When we come over here, 5 minus how many? 7. So this one's -2. And in the middle, we've got 5 minus 4 +1. And on the end, we have 6 minus 5. So -1. Sorry, +1, yes, that's correct. The formal charges have to add up to the overall charge on the ion or molecule. Here it's 0. So all of these add up to 0. So that's a nice indication that maybe we did it correctly. So then we're evaluating these numbers down here. We want smaller numbers. So this one we have -2, +1, and +1. Those numbers are larger than these. Here we have +1, -1, and 0. These are kind of equivalent in terms of magnitude, right? So then the rule is, if there is a formal charge, and this one has to have formal charges, there's no way to draw it without something having formal charges. You want the negative one on the more electronegative element. So here we have the negative on a nitrogen. Here we have the negative on an oxygen. Which is more electronegative? Oxygen. So that tells me that this is the most important resonance structure. It's the most important because it's the most stable. These two are probably going to contribute to it, but this is the most stable. Any questions? Yes?
So at the end is just gonna be which one is more electronegative?
Well, what I'm looking at, first I'm comparing magnitudes of formal charges, and I identified that both of these, the magnitudes are equivalent, right? But the difference is that this one has the negative on oxygen, here the negative formal charges on nitrogen. Oxygen is more attractive to electrons, and so we want negative formal charges to be on the more electronegative element. And so that's how we choose this one over that one. Any questions? You get some good practice on this on worksheet 9. Yes?
So why do we not look at the right ones?
Why do we not consider this as one of the better ones? Because here the formal charges are larger. Here we have a 2. Ideally, we're looking for zeros on everything. But we can't draw one that has zeros. So here they all have formal charges, and one of them's 2. Here, we have the +1s and the -1s, but this guy's 0, and here this one's 0. And so the formal charges overall are lower on the middle one and the left one. Okay? Drawing resonance structures and assigning formal charges for organic compounds. So draw the Lewis structure, including resonance structures for diazomethane, CH2N2, and they're telling us that carbon is central. So you'll often see a little note like this, especially on an exam. We'll give you a clue, because some of these you can draw so many different things that it becomes a little overwhelming. So we're giving you a hint in the right direction. Put the carbon in the middle. And it says, for each resonance structure, assign formal charges to all atoms that have a formal charge. So what that means is if it's 0, you don't have to write anything. You just need to write the actual charges. So if we put carbon in the middle, we've got 2 nitrogens and we got 2 hydrogens, and so they're going to have to be around somehow like that, right? Now, if you drew a nitrogen here and a hydrogen there, or nitrogen here, hydrogen there, it's really the same thing. You would just turn it around and reorient it. Yes?
So I understand that the hydrogens have to be on the outside. Could you also write it like that, but with the bottom end on the other side of the end?
Yes, you could. They're telling us that the carbon is in the middle. They're not necessarily saying that this nitrogen has to be bonded to that carbon, that they both have to. So there are different possibilities. We could put hydrogen up here and a nitrogen here and have the other nitrogen off the side.
And then could you also put C, N, H?
Yeah, you could do it like this. That's
Or
possible.
C in the middle and then N on the other side and then H is on the other side.
Yeah, you could do that too. This one, I'm going to say, let's not even consider this because that's not really having carbon as a central atom. It's one of the central atoms.
I meant N on both sides.
Yeah,
and H.
I know. But I'm just saying, I'm going to erase this one because I don't see any point in keeping that one. And this one also doesn't quite fit with carbon being central, right? So let's get rid of that one. But we could do carbon in the middle, nitrogen on each side. I didn't really mean to draw the bonds. Went back too far. Okay, I lost part of my hydrogen. Carbon, nitrogen, hydrogen, nitrogen, hydrogen. That has carbon as the central atom, right? So let's look at these. Total number of valence electrons. 4 plus 2 plus 10, right? 16. One carbon is 4. Each of the hydrogens is 1. The nitrogens are each 5. So we've got 16 electrons to mess around with. 2, 4, 6, 8, 10. Oops, I didn't want that color. 10, 12, 14, 16. So we've got a nitrogen here without an octet. Can we fix it? If we make a double bond with this carbon, then the carbon's going to have too many electrons, right? So this arrangement is just not going to work at all. You see that? So, we tried it out. It's like, no, that's not going to work. So get rid of him. So 16 electrons. Let's try this other one. 2, 4, 6, 8, 10, 12, 14, 16. So if we move this one in, we could do that. And then we could move this one over here. Is everyone happy there? Yeah. But we could also do, we've seen other ones where we had 2 double bonds, and we saw that we could also do a single and a triple instead. So let's write those. So let's do a triple on that side and a single on this side. And a single on this side and a triple on that side. Yeah, nitrogen does want to form, whoops, only 2 lone pairs. So nitrogen likes to form 3 bonds, right? And carbon likes to form 4. Carbon has 4 bonds in all of these. Here we have 3 bonds for each of the nitrogens. So without looking at formal charges, I'm going to predict that this one's going to come out better. But we actually have to assign the formal charges. So dividing the bonds, Hydrogen never ends up having a formal charge. It can't make two bonds, it has to have one bond, and so it's always going to be zero, so you can just ignore them.
How do you, when you were doing the thing a couple slides ago, when you said how many of this, so it must have this many bonds, how did you do that again?
That was looking at the Lewis structure for the individual atom, and the number of dots that are not paired up is the number of bonds that it tends to form. So nitrogen atoms have 5 valence electrons, and then we're going to subtract the number of electrons that are here. 2, 4, 6. So what's the formal charge on this nitrogen? -1. Carbon has 4 valence electrons, and in here it owns 4 electrons, so it's going to be 0. How about this nitrogen? Yeah, it's got 5 minus 4, so this is +1. And the hydrogen 0. So looking at this one, this is just the reverse of that. So the nitrogen that had the triple bond is +1, and the nitrogen with the 2 single bonds is -1. Let's look at this nitrogen. We take 5 minus 1, 2, 3, 4, 5. So that's 0. Oh, I don't have to write that. Carbon, 4 minus 1, 2, 3, 4, 0. Nitrogen, 5 minus 1, 2, 3, 4, 5, 0. This one has all 0 formal charges. So that's going to be the best one. Winner, winner, chicken dinner. Any questions?
When we're doing a problem like that,
Mhm.
say on the worksheet or something, do we have to show all 3 of them? Like, say if we know which one it is already, we just go straight and do it?
It depends on how the question's worded. This one says, draw the Lewis structure including resonance structures. And so you do have to draw them and assign the formal charges, and that's essentially showing your work. There could be, especially like a multiple choice exam question, that asks you which is the correct Lewis structure based on formal charges. And if you can look at them and do it in your head, that's fine, and you can just pick the correct one. So if it says draw them out, then you have to. If it doesn't, no, you don't. Yes?
And then everything has to follow the octet rule other than hydrogen, right?
Yes. Yeah. At this point, we're obeying the octet rule except for hydrogen. Hydrogen has its own rule called the duet rule.